Good evening, Ireland. It's a pleasure to be back and talk to you about the beginning of everything. Yes, earlier this year I told you about how the universe is going to come to an end. It's a process that will take trillions of trillions of trillions of years. But the beginning of everything is a shorter story in the sense that the universe started in approximately 3 minutes. So this talk is going to be a little longer than 3 minutes, but I'll take you through how it began and how it's evolved since the beginning. If we look out into the sky, we see a universe full of galaxies. This is a 3D atlas, if you like, showing where the galaxies are. You can see they're not uniformly distributed. We're flying through a bunch here, for instance. So although it looks like a simulation, think of it more as a 3D atlas, because here the galaxies have been mapped in their position on the sky and their distance from us. And this fly-through gives us an idea of how the galaxies are distributed. So the question is, how did the observable universe come to look like this? I'll always be talking about the observable universe. We don't know what is outside the sphere that we call the observable universe, and I'm talking about everything we can see in the observable universe. All of the galaxies, the stars, the planets, the gas, the dust. Where did all this stuff come from, and how did it end up looking like this? So we know that a snapshot, such as for instance the Hubble Deep Field series, give us an indication of just how many galaxies there are. A small chunk of sky contains thousands of galaxies, so that gives us an idea that the observable universe contains something like 1 trillion or so galaxies. But we have the question of where it all came from. So I'm talking about the creation of the universe. When did this happen? Well, to the best of our knowledge, it happened 13.8 billion years ago, according to the Big Bang Theory. How long did it take to make this universe? Well, as I will show shortly, it took something like 3 minutes to make all of the ingredients that we need to make the universe that we see around us. Where did the Big Bang happen? Well, it happened everywhere, because I'm talking about the creation of everything. So it didn't happen at one point in space. We can't step out of the universe and say it happened over there. It happened everywhere. Why did it evolve the way it did? Well, because of the laws of physics. And how do we know that it's 13.8 billion years old? And how do we know the way it evolved? Same answer, because of the laws of physics. So one way of thinking about the universe is to say, well, we know what it looks like now. So can we figure out what the rules of the game were? Can we figure out how the universe came to look like the way it does? If we were to look at a snapshot of a chessboard, can we figure out from that picture what the rules of chess are? That's, in a sense, the problem we have. We know what the universe looks like now. We can take a snapshot and we can see the way things are. But does that snapshot help us figure out what the rules are that got us to where we are now? This individual picture of a chessboard does not really help us work out what the rules of chess are. We can perhaps glean a little bit of information from figuring out there were 2 types of pieces, gold and silver, and they seem to occupy different sites on the chessboard, but trying to work out the rules from this one snapshot is very difficult. And similarly, that would be the case if we were to look at, for instance, a picture of a galaxy. We would look at that and say, well, that's very interesting. But from that picture, can we work out how that galaxy ended up looking the way it does? We get the idea that galaxies are actually dynamic. They're actually in motion. They're actually merging with each other. They're rotating. But we can't watch this happen because it happens on a timescale that's far too long. If we wanted to watch this galaxy rotating once, we would have to watch it for 100 million years. So although it would be very nice, rather than take a picture of the chessboard, it'd be very nice to watch a video of 2 people playing chess. That would give us a much better idea of what the rules of the game are. But in a sense, we can't do that. We can only take snapshots. But at least we can take a snapshot such as a deep field like this one And we have the advantage that because the speed of light is constant, if we look at more distant galaxies, we are looking at galaxies as they were in the past. So although it is strictly speaking a snapshot, it is a snapshot taken over a whole range of times, from relatively recent times for the nearby galaxies to very distant times for the very distant galaxies. So we can get a little bit of a cheat and work out how things were at different times. And we can do that with Hubble pictures, and of course more recently we can do that with James Webb pictures. The different distances give us different look-back times, so that gives us an extra angle. But when we look out into the universe looks very complicated. Not only do we have all of these galaxies, what's going on inside galaxies? Stars are forming, stars are living, stars are dying. How can we possibly make sense of all of this? How can we take a picture like that and figure out what the rules of the game are that dictate how we end up living in a universe that has bits and pieces that look like this? It looks far too complex to work out what the rules of the game are. But you have to remember that just because something is complex does not mean the rules that determine that structure are also complex. For instance, we can look at a mathematical set of pixels. This is the Mandelbrot set. And this set of pixels, the colours of each of the pixels that you're looking at, are determined by a mathematical formula. And if we wished, we could zoom in, and it doesn't matter to what extent we zoom in. We could zoom in by a factor of 2, a factor of 10, a factor of 1,000,000, a factor of 1,000,000,000,000. We would still see more and more and more detail. So in other words, the amount of information, the amount of detail in an image like this is far more than I can possibly reproduce in one image. It is many, many trillions of times more than we can see in this one image alone. So how complex must the mathematical formula be that can generate each and every pixel of this incredibly complex structure? You could argue that it's essentially infinitely complex. And even though certain structures seem similar, there seems to be certain repeating motifs in the image we're looking at, they don't actually reproduce exactly. None of these are identical. So just like one star might appear similar to another star, no two stars are identical. So just how complex is the mathematical formula that produced this almost infinitely complex set of pixels that we're looking at? Well, the answer is that. That's the formula that, when applied iteratively, gives us each and every pixel in the trillions of pixels in the Mandelbrot set. So just because the result looks very complex does not mean the rules of the game are complex. One of my favourite quotes from Einstein was the comment that the most incomprehensible thing about the world is that it is comprehensible. And here you can take world as being the immediate world around you, or it can be the Earth, or it can be the galaxy, or it can be the entire observable universe. There is no reason why we are able to comprehend the universe. We're just a bunch of monkeys who came out of the trees 500,000 years ago, and somehow we've managed to evolve into a species which is capable of understanding what we're looking at in the universe and try and figure out how it all came to be. So let me just take you through the flow of thought that helps us understand how the Big Bang happened and how we ended up being here. 100 or so years ago, observations were made that indicate that galaxies are moving away from each other. This is stuff that Hubble started on the Hooker telescope 100 or so years ago. And if galaxies are moving away from each other and the more distant galaxies appear to be receding at greater speed, we come to the conclusion that the universe is expanding. In addition to those observations, we can make observations here on Earth. We can do experiments. We can build ourselves particle colliders, such as the Large Hadron Collider, for instance. We can smash atoms together and see what they're made of, and we find they're made of smaller particles. We can bang them together and see what they're made of. So we can get an understanding of how matter is put together by doing laboratory-based experiments on Earth. But we do have to make assumptions. And the basic assumptions that we cannot prove, but we have to make, are that the laws of physics are immutable. In other words, the laws of physics here and now are the same as the laws of physics somewhere else. The laws of physics in England are the same as the laws of physics in Australia, or Alpha Centauri, or the Andromeda Galaxy. If that was not the case, then we would entirely fail to make any sense of the universe at all if the rules were different everywhere we looked. Similarly, we have to assume that the laws of physics now are the same as the laws of physics in the past and the laws of physics in the future. Again, if it turned out that the laws of physics today are not the same as the laws of physics yesterday, we would have no chance of making any sense of the world whatsoever. If the rug kept getting pulled from under us because the goalposts kept moving, because the laws kept changing, we would not be able to establish any theories which made any sense whatsoever. So we have to make those assumptions that the laws of physics that we understand are immutable. If we do that, we come to the conclusion that the universe was created in a very hot, dense state 13.8 billion years ago, and ever since that time it has been expanding and cooling. So the big question is, when we look out into the universe and we see all of these galaxies and stars and planets and gas and dust, where did all that come from? How far back can we go by thinking about an expanding universe and running it in reverse? How far back in time can we go before we think we're no longer in a position where we think the laws of physics that we understand today hold? How long before we give up? If we go back to the first, let's say, 1 year of the 13.8 billion year history of the universe, are we still confident that we know what was going on? If we go back 13.79999, if you like, billion years, yes, we think the laws of physics were understandable 1 year after the Big Bang. What about 1 day after the Big Bang? What about 1 hour? What about 1 minute? What about 1 second after the Big Bang? Yes, we have good reason to believe the laws of physics we understand today still held at that point. What about the first millisecond? Yes. What about the first microsecond? Yes. What about the first nanosecond? Yes. What about the first picosecond? No, we don't really understand what happened before the first picosecond. There's a sort of watershed in our understanding. Before the first picosecond, before the first 1/1,000,000th of a second after the Big Bang, we are on somewhat shaky ground. We do not know what happened. Why is there a watershed at 1 picosecond? I'll address that point in a few slides' time. Everything from 1 picosecond onwards, that is relatively well understood. Okay, relatively, that's obviously relative to our understanding of various other things, but we think we've got good reason to believe that our understanding from 1 picosecond onwards is relatively firm. So that was a very long, rambling introduction to what it is I'm trying to cover this evening. In the next slide, I'm going to just present a few basic ideas which are rather pertinent to what I'm going to say in the following slides. Some of these things you'll already know, some of the things might be new to you. And then we're going to have a look at the time evolution of the universe, from the first fraction of a second, the first few seconds, the first few minutes. Then we're going to jump a little bit, change gear, and jump ahead to 377,000 years after the Big Bang. That sounds rather arbitrary. It isn't. There's a particular reason for that number. And then again, we'll have to change gear a second time to go fast forward 13.8 billion years to the present. So first, a few basic ideas. Some of these you will be familiar with, some maybe not. So, first statement, we are made of atoms. I hope that comes as no surprise to essentially everybody in the audience. Atoms are made of positively charged nuclei with negatively charged electrons buzzing around them. So, given enough energy, we can take an atom and we can separate it into its component parts, nuclei and electrons. Electrons, as far as we know, are fundamental particles. In other words, they're not made of anything. They are just electrons. You can't take an electron, cut it in half, look inside and see what it's made of. As far as we know, you can't do that. A nucleus, however, is made of smaller stuff. You can take a nucleus and start picking it apart. And we find that nuclei of atoms are made of particles that we call protons and neutrons. Now, as far as we can tell, the same is true. Protons and neutrons are not fundamental. They're not like electrons. Protons and neutrons are both made of something smaller. For instance, we can take a proton, we can look inside it, and we find it's made of smaller bits. Those bits are called quarks. We're not going to worry about why they're called that. We're just going to take this sort of Russian doll model of things being made of smaller things down to this particular point. As best we can tell with current technology, we cannot go any deeper than the world is made of quarks and the world is made of electrons. 3 quarks make a proton. A neutron is the same. A neutron is also made of 3 different quarks. Protons and neutrons together make a nucleus. Nucleus, when combined with electrons, gives you atoms. And of course, atoms combine together to give us molecules, and molecules combine together to give us. It takes a certain amount of energy to break an atom apart to make a nucleus and electrons separate. It takes more energy to take a nucleus and break it down into its component parts. It takes even more energy to take a proton and look inside it to see what it's made of. So there's an implicit energy scale here. From low energy at the top, more and more energy is required as we go deeper and deeper and deeper into the nature of matter. Now, as far as a physicist is concerned, if you've got a lot of stuff with low energy, that corresponds to a low temperature system. And if you've got a lot of stuff with high energy, that corresponds to a high temperature system. So there's an implicit temperature scale here as well. Cold at the top and hot at the bottom. But remember what we just said a couple of slides ago, the universe was made in a very hot state and has been expanding and cooling ever since. That means there's a time scale running from hot to cold, from the bottom of this picture to the top of the picture. So what that means is, in the very early universe, for instance, atoms couldn't have existed because the universe was so hot you couldn't take a nucleus and electrons and put them together to make an atom. There was so much energy around in the early universe, they would have shaken themselves apart. Similarly, nuclei didn't exist in the very early universe. If you tried to make a proton out of 3 quarks, there was so much energy they would just shake themselves apart. And you couldn't possibly put a proton and a neutron together to make a nucleus because there was too much energy. So as the time scale runs from hot at the bottom to cold at the top, we can see that we have to wait until the universe is cold enough for quarks to make protons, and then it has to cool a little bit further until protons and neutrons can make nuclei of atoms, and then it has to cool a little bit further before nuclei and electrons can get together to make atoms. So the universe was made from the bottom up. That's the basic concept that we're going to stick to for the next few slides. So where do we start? Well, I guess we start with what we don't know. What happened at t equals 0? What happened at the instant that the universe was created? Well, no surprise, science cannot provide a definitive answer. We can hypothesize as to what might have happened at t equals 0, but we have no evidence telling us one way or the other what actually happened. It's believed by a lot of people that maybe it was a quantum fluctuation. Quantum theory says that you can have fluctuations, essentially fluctuations in nothing. One way of thinking of it is to say that you can borrow energy from nothing and then pay the energy back again. As best we can tell, quantum theory has been saying this has been happening forever, and quantum theory has been tested over and over and over again for the last 100 years, and nothing so far has proven quantum theory wrong. So maybe it is possible to borrow energy from nothing as long as you pay it back. Now, this sounds really weird, but then quantum mechanics is weird, and I'm not going to go any further into quantum mechanics. But you can ask, well, how big a quantum fluctuation can you have? If you start with nothing, how much can you borrow from, if you like, the bank of nothing before you have to repay the loan? Well, the energy that you borrow multiplied by the time that you have to repay the loan, that product, energy time time, has an upper limit. But even though you can borrow a lot of energy for a short time or vice versa, working out how long we have to repay the loan depends, of course, on what the total energy that we've borrowed is. And the curious thing is, if you work out the total energy of the universe, all of the gravitational energy from all of the objects that we see, and all of the mass energy converted, as it were, through E equals mc squared into an equivalent energy, when you add it all up, the answer is apparently 0. So if the total energy of the universe is 0, maybe the length of time we have to pay back the loan is actually infinite, because we've actually borrowed a total of 0 amounts of energy. That almost certainly sounds like a cheat, and that's unfortunately the way quantum theory works a lot of the time. But remember, this is hypothesis. We do not know what happened at t equals 0. So let's move forward. Let's move forward a relatively short length of time. The length of time indicated in the box at the top there. T equals 0.000, lots of zeros, 1 seconds. So this is the unimaginably early time of 10 to the minus 35 seconds. And the universe has expanded from nothing to the size of a golf ball. And interestingly enough, just like a golf ball, the universe has dimples. Well, okay, not dimples in the same sense that a golf ball has dimples on the surface, but the universe does have small variations of density and temperature across its volume. So we can think of them as dimples, but remember, it's not an exact analogy. But there are small variations in density as the universe is expanding. It's difficult to get your head around this concept of the universe being the size of a golf ball. What we're saying is that everything that is currently inside the observable universe, currently tens of billions of light years in diameter, everything that is currently in the observable universe used to be a lot closer together, used to be separated by centimeters rather than tens of billions of light years. It's difficult to conceive just how dense this golf ball would have been, but although we can put a number on it, there's no point in trying to imagine it. So these dimples, these variations in density that exist in this very early cosmic golf ball, when the universe is much, 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 much bigger, these variations in density, these dimples, will ultimately give rise to the formation of large-scale structures in the universe, clusters of galaxies and individual galaxies. Let's move forward again. We're now moving forward to the first picosecond, 10 to the minus 12 seconds. 1 picosecond after creation, the universe has expanded until it's approximately the size of the solar system. Yes, of course, the solar system doesn't exist yet and won't do for a long, long time, but that just gives us an idea of how much the universe has expanded. From the size of a golf ball to the size of the solar system in a tiny, tiny, tiny fraction of a second. So yes, of course, the universe must have expanded much, 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 much faster than the speed of light. And indeed, bits of it are currently expanding faster than the speed of light. At this point, 1 picosecond after the Big Bang, the temperature has fallen to about 10 to the 15 Kelvin. and the energy of each of the particles that could be created. If you borrow some energy, you can make matter. We'll come to that in just a second. But if you think of all of the particles that can be created with the energy that you've borrowed, these are electrons and quarks. Let's just think of it as a quark soup for the time being. All of the individual constituents that exist at this very early time, they will all have an energy which is comparable to the energy of the particles created in the Large Hadron Collider. In other words, the Large Hadron Collider can effectively generate temperatures equivalent to 10 to the 15 Kelvin. So that is why we say that this is a watershed moment. From this moment onwards, from the first picosecond onwards, the particles that existed in the early universe being created from the energy that we've borrowed, they are of an energy that we can recreate in the laboratory. And hence we can test our ideas. We can make predictions and say, if this was the case, this is what we ought to be able to observe in the laboratory. And hence we have testable ways of saying this is not simply a hypothesis, this is a theory which can be tested against observations. So from this point on, we have a reasonably good idea of how the universe evolved. Excuse me just one second. Okay, so we've borrowed some energy, and energy and matter are continuously changing back and forth. We know the exchange rate, E equals mc squared, that tells us a certain amount of energy can create a certain amount of matter, back and forth, back and forth. Actually, we don't just generate matter, we generate matter and antimatter, originally in equal amounts. Antimatter is just the equivalent of matter, but with the opposite electric charge. In other words, an electron has an anti-electron equivalent. It's, to all intents and purposes, the same as an electron, except instead of being negatively charged, it's positively charged. Every particle in existence has an anti-particle equivalent. And we just bundle all those antiparticles together and call it antimatter. So what was happening was a certain amount of energy. I don't know how to represent energy as a picture, so I'm just going to represent energy as a big capital E, because my imagination is not good enough to think of something else. So a certain amount of energy was used to make matter and antimatter, for instance, quarks or antiquarks, or possibly electrons and anti-electrons. Probably not a tangerine and an anti-tangerine, but the point is it doesn't matter, if you'll excuse the pun, what was actually created. Energy created something, some particle, and its antiparticle equivalent. Maybe a quark, maybe an electron, maybe a more exotic particle. But once you make a particle of matter and a particle of antimatter, what happens very soon thereafter is they annihilate and produce energy. And this will be going on backwards and forwards and backwards and forwards. Once those matter and antimatter particles have generated energy, that energy can go on to make a different particle and a different antiparticle. Okay, yes, it's unlikely to be a hot dog and an anti-hot dog. Almost certainly it'll be quarks and electrons and other fundamental particles. But the point is, it'll be happening backwards and forwards and backwards and forwards. Energy and matter continually exchanging back and forth. Via some process that we're still trying to understand, although originally matter and antimatter were made in equal amounts, somehow matter gained a very small excess over antimatter. So what that means is, instead of generating equal amounts of matter and antimatter, slightly more matter was made than antimatter. So what that means is, if we think of the first particle pair, we've got matter and antimatter, they're going to make some energy, and similarly that matter and antimatter are going to annihilate and make some energy. This energy will probably be in the form of radiation, so let's just think of that in terms of gamma rays, for instance. But of course, on the right-hand side there, we have a particle of matter, and because we have an imbalance of matter and antimatter, this has got nothing to annihilate with. So that means that we end up with a universe which is full of energy and a little bit of matter, the bit left over. And we can think of all of these particles of energy as being photons of light. So think of each of these as being a photon, which is a gamma ray, and a little bit of matter left over. That is the matter that makes all of the galaxies and all of the stars and all of the planets and you and me. I've indicated here that the matter-antimatter excess was something like, 10% in these icons I put on the screen. But actually the imbalance wasn't 1 part in 10. It was actually about 1 part in 1 billion. So in other words, we live in a universe in which there are something like 1 billion photons of light for every particle of matter. Radiation outnumbers particles in terms of photons of light versus particles of matter. But it's just as well there was an imbalance, otherwise we wouldn't have that tangerine left at the end, which makes everything we see in the observable universe. Let's move forward to 1 millisecond, 1/1000th of a second. Matter and antimatter are continuing to pop into and out of existence. Eventually, it's possible for the quarks that are made by the energy creating matter and antimatter, it's possible for those quarks to get together and make a little group of 3 quarks, and a particular group of 3 quarks is a bag that we call a proton, and a different combination of 3 different quarks is a particular particle that we call a neutron. So we don't have to worry about the details. This is not a lecture on particle physics per se. All we have to worry about is that if we make enough quarks, some of them are going to get together, and a certain group of 3 quarks is what we call a proton, and a certain group of 3 different quarks are what we call a neutron. I'm not going to explain why we've coloured them different ways, and I'm not going to explain what the U and the D symbols mean. All that matters is that this group is not the same as that group. They're similar, but not the same. And that means protons can change into neutrons and neutrons can change into protons. If there's enough energy knocking around, which there is at this 1 millisecond point, it is possible for these particles to change, because the particles can change into energy and energy can change back into different particles. So protons and neutrons are changing back and forth and back and forth. Let's now go forward to 1 second after the Big Bang. The universe has now cooled down a bit, and it's now only about 1 billion Kelvin. It's now too cold for protons and neutrons to readily swap backwards and forwards. That was possible a little while ago when the universe was much hotter, but now the universe has cooled a bit. It's no longer possible for protons and neutrons to swap back and forth. Now we know that protons are a little bit lighter than neutrons, by about 0.1%. How do we know that? Because we can measure that in the laboratory. And remember, we're assuming that a neutron and a proton 1 second after the Big Bang are not, in essence, any different from the protons and the neutrons that we can observe in the laboratory today. So if we know that protons are a little bit lighter than neutrons, protons represented by the red dots and neutrons represented by the blue dots, if we know that protons are a little bit lighter than neutrons now, that must have been the case in the early universe. And when protons and neutrons can no longer swap back and forth, their numbers would be frozen, and the ratio of the two would be in favour of the protons. There would be more protons than neutrons in the ratio of about 75 to 25. Why are they not made in equal numbers? Because the protons are lighter, and so they're easier to make. Nature always favours the lower energy, and because E equals mc squared, you can say that means nature always favours the lower mass. So because protons are slightly lighter than neutrons, we can calculate how many are likely to be made according to the laws of physics we understand today. And it turns out the ratio is about 75 to 25 after 1 second of the universe's existence. But it doesn't stay quite at that ratio, because we know that after of order minutes, We know that neutrons are unstable and some of those neutrons will change into protons. How do we know that neutrons are unstable? Because we can observe that in the laboratory today. And the neutrons of 13.8 billion years ago are no different. So we know that some of those neutrons will have changed into protons, and after a couple of minutes, that ratio that we showed just a minute ago of 3/4 protons, 1/4 neutrons, that's now changed. Notice that 2 of the blues have now changed to reds. So the ratio of protons to neutrons is now 14:2. Out of choosing 16 arbitrary particles, 14 of them will be protons and 2 of them will be neutrons. What happens next? Well, after 2 to 3 minutes, the universe has cooled down to about 100 million Kelvin. It is now possible for the protons and the neutrons to get together. Up to this point, if you tried to get a proton and a neutron together, they would have had too much energy and they would just fly apart. But now the universe is cold enough that if you put a neutron and a proton together, they will stick. They will bond together. They will make a very stable particle. And so the protons and the neutrons are going to start to combine into the most stable particles that they can make. What that means is they will make an awful lot of this. 2 neutrons and 2 protons. So as indicated on the right-hand side here, 2 protons and 2 neutrons is one of the most stable structures that can be made. And with enough neutrons, the entire universe would turn into these particles, which we would either call alpha particles or we would call them the nucleus of helium atoms. But notice that we haven't got enough neutrons to go round. We can't pair up 2 neutrons with 2 protons across the entire universe. We've got them in the ratio of 14:2. So the best we can hope for is that 2 protons and 2 neutrons get together to make the nucleus of a helium atom, a very stable alpha particle. But that leaves us with 12 bachelors who can't find any neutrons to pair up with. So that means that if the Big Bang theory is correct, the universe should be full of hydrogen and helium, and this ratio that we've shown here does not change after the first 3 minutes. Once 3 minutes are up, the universe is too cold to change that ratio any further. So in other words, the relative abundance of hydrogen and helium in the universe is dictated by what happened in the first 3 minutes. And we would expect, according to the Big Bang theory, to have a universe which is 3/4 hydrogen by weight, by mass, 3/4 hydrogen and 1/4 helium. So there's obviously more individual hydrogen atoms or nuclei, but they are lighter than the equivalent nucleus of helium. So if the Big Bang theory is correct, the universe should be full of 3/4 hydrogen, 1/4 helium. When we actually look out into the observable universe, what do we see? We see a universe which is 3/4 hydrogen and 1/4 helium, and a tiny, tiny amount of other elements. So that's one of the reasons that we think the Big Bang theory is correct, because it predicts the relative abundance of the elements. Now, for those of you who know about stellar evolution, we know that stars are converting hydrogen into helium. True, but stars haven't had very long, they've only had a few billion years, so actually most of the hydrogen is still as it originally was when it was made in the Big Bang. Only a tiny fraction of that hydrogen has actually been converted into helium in the cores of stars that have been burning perhaps for many billions of years. So one of the strengths of the Big Bang is that particular prediction, that after 3 minutes all the action is effectively over. So we're now going to make a big jump into the future, because nothing much of any interest happens for the next 1/3 of a million years. The universe goes on expanding. The universe goes on cooling. But something important happens after 377,000 years. At that point, the universe cools to a temperature of about 3000 Kelvin. Why is 3000 Kelvin important? Because that is the temperature at which a positively charged nucleus, like a proton, the nucleus of hydrogen, or an alpha particle, the nucleus of helium, this is the temperature at which a nucleus can start to capture an electron. A positively charged nucleus can capture an electron, which can then orbit around the positively charged nucleus. Prior to this point, the universe was too hot for atoms to form. If a positive and negative charged particle came close, they would be so energetic the atom would be instantly ionized and the positive and negative charges would go their separate ways. But from this point onwards, the universe is cold enough for positive charge and negative charge to get together. So nuclei can now hang on to the electrons that are floating around in the soup, and so this is the point at which atoms can actually exist for the first time. Up to this point, there have been just nuclei and electrons. So the universe changes from being a plasma of positive and negative charge to a collection of atoms, a collection of neutral atoms, because the amount of positive and the amount of negative are balanced in every atom. At this point, the universe becomes transparent to light. So up to this point, light has been bouncing around like a ball in a pinball machine, and it found it impossible to escape the plasma. But as soon as the universe becomes transparent, because positive and negative charge can get together to form atoms, that light that was trapped in the plasma is now released to fly across the universe. And that is the light that we see as an afterglow of the Big Bang. When the universe was 3000 Kelvin, most of the light would have been produced in the visible part of the electromagnetic spectrum. When you heat an object up to 3000 Kelvin, it glows white hot. It generates lots of visible light and some UV and some infrared. But most of it will be in the visible part of the spectrum with a wavelength of order microns. And that light we can see today, but the universe has expanded since this point in time. The universe is now 1,000 times bigger than it was, so the wavelength of light has expanded 1,000-fold. So instead of the wavelength being microns, the wavelength is now millimeters, 1,000 times longer. So we don't see it as visible light, we see it as microwaves. So this is the origin of the cosmic microwave background. It's the afterglow of the Big Bang, the light that was released some 377,000 years after the Big Bang, and we see the microwave background coming from all directions on the sky. This is an all-sky map where the whole sky is unwrapped into this particular oval shape. But we notice that although it's essentially the same intensity in all directions, there are some small variations which have been exaggerated in this particular image. Some parts are slightly higher intensity, shown by the red dots. Some patches are lower intensity, shown by the blue. And different intensities correspond to different temperatures or different densities back when the universe was much smaller. If you remember the cosmic golf ball with the dimples were variations in density or variations in temperature. And that's precisely what we're looking at when we look at these fluctuations in the cosmic microwave background. They're only small fluctuations, they're only a few parts in a million, but they are measurable by the satellites that have measured the cosmic microwave background. And because this is giving us the picture of the early universe, it's rather important that we study the cosmic microwave background. Because it's not perfectly smooth, these variations that we see in the map that I've just shown you basically map on to the dimples of the cosmic golf ball. And that's why satellites like Planck, for instance, have been used to study the cosmic microwave background, because it gives us a picture of the very early universe. As far as electromagnetic waves are concerned, that's the earliest part of the universe we will ever be able to see, 377,000 years after the Big Bang. We'll never be able to go any further back than that. So these dimples in the golf ball, I said that they gave rise to the variations in the cosmic microwave background and eventually gave rise to variations in the large-scale structures of the universe. And we can see that in a simulation if we just take a small volume of the golf ball and seed it with very small variations in density or temperature and then let gravity do its stuff. We find that gravity exaggerates the small variations in density, and we find matter starts to clump together. And here the brighter regions that we're looking at, seen over billions of years, correspond to increases in density that will ultimately give rise to galaxies and clusters of galaxies. Notice that we get a cosmic web. We see galaxies at the intersection of particular regions which look like filaments, and we see regions which look relatively empty and other regions which look very clumpy. If you remember the 3D atlas that I showed at the very start of this talk, that's precisely what we see when we look at the galaxies spread across the universe. They're not uniformly spread, they are clustered together. There are occasionally filaments, there are occasionally voids where there are very large regions where there appear to be very few galaxies in existence. And according to these computer simulations, this is precisely what we expect if we start with a cosmic golf ball in which there are very small variations in density and we let gravity take hold. Then the simulations tell us that we should end up with a universe that looks much like the universe that we actually see. So that gives us an idea that the Big Bang theory is probably the right theory as best we can tell at the moment, and it gives us some confidence that the simulations that we're running to say how did we get from the very early universe to the universe that we see today, those simulations do seem to be mapping out the rules of the game which have some meaning. If we ran these simulations and we could never get a universe similar to the one we see today, it would tell us that we've got the rules of the game wrong. So the fact that the simulations seem to work gives us some confidence we're doing the right thing. If we were to look at a map of what's going on in our local neighbourhood, here's the Milky Way and a few minor galaxies, a few dwarf galaxies surrounding us. There's the there's the Andromeda galaxy not so far away. This is the local group of galaxies containing a few big galaxies and a lot of small galaxies. If we change the scale, so the local group is now just in the centre of this region, we see that we are in a sense part of a rather large filament of galaxies and clusters and superclusters of galaxies. We can see some regions that seem to be relatively sparsely populated with galaxies, and we see the Virgo cluster, for instance, and we see the Fornax cluster, and we can see that they are in very loosely, not a straight line, but a cluster that indicates there's a filament of clusters, much as we saw in the previous simulation. If we go out one more scale, there's the Virgo supercluster right at the centre. And again, when we look at where galaxies are positioned in three-dimensional space, we find that there are filaments and there are voids, just like this large void here, the Boötes void, where there seem to be very few galaxies in this particular region of space. And remember, the simulations tell us that this is all a natural consequence of the variations in density in the very early universe, giving rise, once gravity is given time to do its stuff, then it will produce these filaments, these clusters and these voids, and the overall web structure that we see in the universe today. So what happens in the next 13.8 billion years? Well, if we understand the origin of hydrogen, and we think we can understand hydrogen because once you make a universe, hydrogen seems to pop out after 3 minutes or so. Once you've got a universe full of hydrogen and some helium, well, that means that you can start to understand galaxies through simulations and through the laws of physics. If you've got hydrogen, you can understand galaxies and stars and planets and trees and mountains and snowflakes and rainbows and cats and Okay, maybe not cats. I don't think we'll ever understand cats. But once you have hydrogen and once you have the rules of physics that we understand today, most things start falling into place. Yes, there are some details of cosmic evolution that we have yet to work out. But if you start with the universe full of hydrogen, you can understand a lot about the way things are. Let me just remind you what the timeline is. This is a very non-linear timeline. The universe started, we don't quite know how, but after 10 to the minus 35 seconds, it is hypothesized that we end up with everything currently in the observable universe would have been only a few centimeters apart. The energy that we borrow is enough to make us lots of matter and antimatter, and we end up with a soup of quarks and electrons and probably other particles, but let's just call it a quark soup because it's easier. After a little while, the universe is cold enough for the quark soup to make protons and neutrons after a few seconds. And after a few minutes, it's possible for those protons and neutrons to get together and make nuclei of hydrogen. Any protons left over are what we would ultimately call the nuclei of hydrogen atoms. If we wait 377,000 years, then those nuclei will grab hold of the negatively charged electrons to make atoms. The light will be released, and the visible light is seen by us today as microwaves, the cosmic microwave background. That happens at a fraction of a million years after the Big Bang. We don't know quite what happens next. There are the dark ages. Sometime after the microwave energy is released, it'll take a little while for stars and galaxies to form. So we know that after a while, after billions of years, galaxies form. But what we don't really understand is the details of what's going on here. Before the first stars form, the so-called dark ages, we don't know what's going on. We don't know quite how long it takes for the first stars to form and the first galaxies to form. That's one of the reasons the James Webb Space Telescope is looking back to these early times, a few 100 million years after the Big Bang, before the formation of the first galaxies, so that we can understand the formation of the first stars, the first galaxies, the first supermassive black holes. So hopefully in a few years' time we'll have a better understanding of this period here. We still have a few things to work out. The jigsaw is not complete. There are some rather fundamental questions still remaining. Why did matter win over antimatter? It appears that it did because we are here and the observable universe is dominated by matter. There's only a little bit of antimatter floating around. So what caused that original asymmetry? We can study the asymmetry using particle physics, but we don't necessarily understand the origin of it. And what is dark matter? So I have said nothing about the nature of dark matter that's causing galaxies to rotate at speeds which look at first sight to be wrong. And also dark energy. Something is out there causing the universe to accelerate its expansion. I've been talking about the beginning of everything, but I've tried to be very careful to make it clear that I've been talking about everything that we see in the observable universe. All of the galaxies, all of the stars, all of the planets, all of the dust, all of the gas. I have not been talking about dark matter and dark energy. So when I say the beginning of everything, really I mean just the 4% that we can actually make sense of. The other 96%, the dark matter and the dark energy, is still a bit of a mystery. But, as they say, that's another story. Thank you for listening.